lecture 1. So where is this application and state of the art? Yeah, I mentioned in the previous lecture, and also show you some application and show the video as well. And these are some advanced application for intelligent system or artificial intelligence, like recommender system, that they use collaborative filtering, like Amazon, Netflix, usually the e-commerce companies, they provide or they develop the recommender system. Then when you come to the website of the this application or e-commerce, and they will give us the notification after that. So what kind of product that we are interested in actually. So then later, they will they will give us the notification, regarding the related things that we are interested in. So like Netflix, for example, then they will provide information about the new movies that have been added in Netflix that actually related to our interest, for example. And Amazon or let's say Alibaba and so on. So then they will provide us the notification after we visited some product or interested site of the product. Then after that, they will send us the notification if there is a new product related to our interest. And then, of course, they encourage us to again explore his e-commerce sites, and after then do some or perform some transaction. And spam filtering in Gmails also use artificial intelligence, and machine translation. So I shown you before the conversation between a human and machine. In this case, Google, Google for the purpose of the translation. Okay, so we check the video. It's work or not?
Monzo.com makes dance great again. Yeah, you know what? I'm not going to say again because I never were. And
you have international friends talking smack behind your back. You use Google Translate. You're looking up words for a French class you regret taking. You use Google Translate. You're in a foreign country and just want to ask a waiter for some extra cheese on your taco. You use Google Translate. Google Translate has quite the eclectic of applications.
Okay.
But
can you see the
how does it
video?
How is that all work?
Yes, sir.
Good.
Yes, sir.
We're going to answer these questions today. Techie or non-techie, I'm going to make sure you all follow along and learn something interesting in the end. This is Code Emporium. And with that, let's get started. Language translation. How do we translate a sentence in one language to another language? To make things concrete, let's say that we're translating from English to French. Our first trial would be you take every word in the English sentence. For every word, you find the corresponding French translation, then spit it out. And we repeat this for every word in the sentence. It's a simple strategy, and honestly, we don't need machine learning for this. If we just have a curated database with English to French word translations, then we're all set. For every English word, look it up in the database, get the corresponding French word, and repeat this for every word. That's great, but there's a problem with this. If you're bilingual, or even if you just know English, then you know that language has two important components. That's tokens and grammar. Tokens are the smallest units of language. Grammar defines how these tokens should appear so that they make sense. So in this context, tokens are words. Every word is a token. It's a beautiful day has 5 word tokens. And grammar is basically a guide or a set of rules that defines an ordering for these words. If language was constructed from tokens and grammar didn't matter, then language translation would be so much easier. And our simple word translation system we came up with would actually be the state-of-the-art translator. However, that isn't the case. Grammar exists and we need to incorporate it in translator logic. In order to incorporate grammar, we have to ensure many things. The first is syntax analysis. Syntax is basic structure. It's basically asking the question, does the structure of the sentence look correct? In English, we could have an adverb followed by an adjective followed by a noun, like very big cloud.
So in this case, if we don't care about the tokens and grammar, then we can usually just simple, algorithm, yeah, you just take the complement or the translation. So then we don't use any grammar, yeah. But then in this situation, because we have to consider about the grammar, so then the system becoming complex, yeah. So we have to apply some machine learning, yeah, in order to give an appropriate result, yeah, for the translation, yeah. So if we proceed for some video,
And
then
then we have
we can
semantic
see
analysis. Semantics is
some
and
configuration,
it asks the
some
question,
consideration
does
about the
sentence make sense in context?
grammar here, like syntax,
If we don't
semantic.
follow this,
Yeah.
then we're just outputting gibberish. Language translation adds to the chaos as we need to make sure the translated French sentence follows the similar rules. Clearly, language is more complex than simply an assortment of tokens. Instead of trying to explicitly define our own grammar, what if we let the machine's neural network do it for us? If you haven't heard of neural networks, don't worry about it too much. Just think of it as a component that learns to solve problems.
So
by
this is one example that
hundreds
the
of
system
systems
using a
analysis.
neural network,
This is a network to
yeah,
learn
to
patterns in
perform
data
machine
and
learning
eventually it will be able to
tasks.
translate a given English sentence to French, all on its own. Now, this sounds interesting, but what exactly is this network? Now, we can actually derive the neural network architecture required based on the problem we are trying to solve. In this case, we need a neural network that solves the problem of language translation. Some English sentence is the input and it should spit out some French sentence. The first thing you notice, the input and outputs are both sentences, or a sequence of words. But computers don't understand sentences like humans do. So we need to convert it into a form that they do understand, and that's numbers. More specifically, vectors and matrices, which are just an assortment of numbers representing data. And so we have the first part of our network, a sentence to vector mapper. This part of the network takes an English sentence and spits out a vector of numbers that the computer can understand. Now this box here is a neural network. And since we're dealing with sequences or sentences,
All right, so these are some initial illustration about the language translation using neural network. So then we'll continue later on, this part, because of I think we have a topic about the neural network as well. Yeah. So then we will discuss about this later. All right, so we continue with the slides and speech recognition. I see this is the common thing that we use actually, yeah, because we already use some application of speech recognition like Siri, yeah, in Apple, iPhone, Google No Cortana in Microsoft, yeah, and Echo in Amazon, and also the Google Duplex. So it actually leverages the deep neural network, yeah, to handle the speech recognition and the natural language understanding. And then the other application is handwriting recognition. So we can perform offline or online for handwriting recognition. Yeah, and then this one is a machine learning applied to hand drawing. Yeah, so in this example, we can use auto draw. Yeah, so then we just write normal drawing, or we draw just the normal one here, and after that, the machine, you know, or the computer will generate computerized drawing. Yeah, the right side. And Google Quick Draw also we can do. Yeah, can perform. Yeah, draw some or one device, and then after that, the machine will generate some option, yeah, according to the original drawing. And then face detection, yeah, detecting if there is a human face, yeah, this is using the common method like Viola Jones method, yeah, and you can see the project axis, yeah, for face detection here, yeah, and also face recognition, yeah, it recognizes the face, yeah, and much more challenging problem this one, because we will you know, use many features, yeah, more complex than the detection. Detection just recognize, okay, this is the human face or not. Yeah, but face recognition, we have to, you know, provide some database, you know, for the human face, and after that we perform like of pattern matching, yeah, in this face recognition. And if some features match with the available database, and it will give us the percentage of the matching. Yeah, for example, for 95% or 99% of the similarity. So yeah, you can see this video, yeah, by yourself, yeah, because I already sent you the slide, yeah, for face detection and also face recognition. Then you can see the difference, yeah, between detection and recognition. And then generating tuning realistic artificial faces, and it uses generative adversarial network, yeah, or GAN, yeah, for tuning realistic artificial faces. Yeah, then you can see some information here, read the references, yeah, in order to understand about the GAN. Yeah, and also the deepfakes, this one, yeah, we have some information or references and examples, and you can see here. Yeah. So in this article, yeah, it mentioned about 20 of the best deepfake examples that verified and use the internet. Yeah, so then you can know more about the deepfakes. And then in 2015, a single general learning system, it called as DeepQ network, DQN. It can learn directly from experience to master a wide range of challenging tasks, yeah, like the games in this case. So we can see this example in the video here. So you can just click and see the DeepMind, then that they perform the to play the Atari games, and also the reinforcement learning, yeah, for playing games. So machine learning is very, you know, interesting. Then some researchers apply this kind of technique, yeah, to develop uh, the, the games, yeah. So to develop the games to be more realistic and interactive. And Google AlphaGo, yeah, in March 2016, yeah. So with much bigger search space, yeah, and the computer beat South Korean Go champion. Yeah, so then you can see also the video. And CMUs, yeah, Carnegie Mellon Universities, Libratus, yeah, for poker playing AI, yeah. They found this AI application in January 2017, and this is actually one of the hardest games for AI, yeah, to solve or to crack the large state space, partial information, bluffing, and misleading information. If you want to know more, then you can just see the video here. Yeah, this is the anecdote. Yeah, so like as we know that the humans are hooked. Yeah, so humans are addicted actually with this gadget, but the machine start learning. Yeah, so exchange between the human and machine. Yeah. And then the other application, yeah, the most interesting, yeah, in my opinion, is in robotic, yeah, because of since my research interest also in robotic, so this application considered as the most interesting in artificial intelligence. Yeah, as you can hear, I want to show you this video, yeah, for future military robots. Can you see the video? Can you see the video right now?
Yes, sir.
Okay, good. These are some examples of application of the robot, yeah, yeah, for the exploration or even for the military purpose. So this robot is working in rigid, I mean the you know, any environment here. Yeah, so it can walk on the top of water, rock, uh, land, yeah, even on the top of desert. This robot called Sunfly, so it can jump and reach the higher surface here. And it can return back to the original position. It is robust, so even though it's quite high, jump quite high, but still the body and all the mechanical part still working well. So this robot is called Big Dog, developed by DARPA as well for usually to bring or expedite some materials, or logistic here. Even with the heavy load, so it can work, with any condition and environment. All right, so if you want to know more, then you can just see the video. And then the strong AI for full AI or artificial general intelligence or AGI is an intelligence of machine that could successfully perform any intellectual task that the human can do. And strong AI should be able to reason, solve puzzles, for example, make judgments, plan, learn, communicate, and have consciousness, self-awareness, sentience, and sapience. That's why in the future, then even accountant or lawyer, it can be replaced by the AI algorithm, since the AI right now more strong or stronger than the previous one. So then it can perform complex tasks or works that human being can perform or can do. And then the weak AI also, so there is applied AI or narrow AI. AI focus on one narrow task, only the small task or specific task. And machines can only simulate the mind or real intelligence, but they cannot create a real mind or consciousness. Only just to duplicate, or simulate the mind. Right. So these are the history, the brief history. It started in 1940 up to 50, gestation of AI. Initiated by McCulloch and Pitt Neuron, with the Turing, also the Turing computing machinery and intelligence. So you can read more here, the articles about this initiation. And then in 50 to 70, early enthusiasm for or great expectation in AI. So the AI programs, Samuel Checker program, birth of AI, actually in Dartmouth workshop in 56. This is we can say the birth of AI. And you can check this video, The Thinking Machine, by MIT in 90s. And 70 to 90, knowledge-based AI is started. So with the expert system, at that time, AI becomes an industry. You can see in this video, AI Winters, and that actually the illustration of knowledge-based AI. And the mid of 90s, they'll present scientific approaches. So many development have been done, and even very progressive in this area. Neural networks return to popularity with the propagation algorithms, and also the emergence of the intelligent agent started in 1995 until present. And AI becomes scientific even in daily activities. We use AI right now, with deep learning, big data, and so on. Is AI another inflated hype? The recent comeback of AI methods prove very effective for many applications today. So could it be an inflated hype? Will there be another AI winter? So we can read this kind of information from this article, like AI mid 2021 with the self-driving car meets the reality, and AI winter is coming. Why AI is harder than we think, and AI winter is well on its way. And then this is the map of AI. So AI with knowledge representation here. It has many branches here. So then from the machine learning, robotics, programming languages or tools, hardware, and then representation method, knowledge engineering, vision for application, and also image processing agent, neural network, natural language, heuristic. So these are the branches of the AI. So it developed to advanced thing even until today and the future as well. Right, so these are the distribution of delivery of our course here. So the introduction, intelligent agent today, we will talk about the intelligent agent and solving problems by searching. So we have 3 topics about this: evolutionary computation, or related topics, and neural networks, and knowledge representation, reasoning, and introduction to product. But then maybe I'm going to introduce some other platform for developing AI, because a Prolog is actually very old. This one is a long time when I was in even I think around 2000, the year of 2000 started. So then it's been a long time. So then I'm going to introduce a different thing in this course. But Prolog still, I will introduce the Prolog, and also we use a different platform to develop AI like Colabs. So Google Colabs. So Google Colabs actually based on the open platform. Then we can easily use this platform because it is open source. Yeah, with Python based programming. But then in Google Colab we can use the toolbox available. So for the beginner, we can easily understand how to construct the system, especially for AI application. So we'll learn AI fundamentals. Even though we will not cover this topic, but of course I will show some application like was it the pattern recognition for image processing, image recognition, for example. And if we have time also, I will introduce voice recognition as well, but it depends on the time duration that we have. Right, so finish the first topic, first lecture, then we proceed with the second lecture. So any question or any comment with the introduction part? I have shown many videos and also some application in order to give more perspective about the application, because of today actually we interact and we use AI in everyday activities or in everyday life. So any comments? Not yet. Okay. All right. So then we continue with the second topic here. Second slide, second lecture, right? Can you see the slides here?
Yes, sir.
All right, good. So intelligent agent. So at the end of this lesson, students should be able to define the intelligent or rational agent is the definition, and also describe the agent task environment and its characteristic, and determine task environment characteristic for a given intelligent agent, and identify different structure types or design of agent programs and their capabilities. And so this material is actually taken from this book, Artificial Intelligence, a Modern Approach, that edition. Okay, so I will show you the textbook as well. We have for this course, because mostly we take the materials from these textbooks. I will show you first the textbook that we have. Actually, there is artificial intelligence modern approach of fourth edition. So the latest one. So we can refer to this edition. So can you see the PDF here? The books.
Yes,
Yes, sir.
All right. Okay, so this is the textbook that we use. Artificial Intelligence, Modern Approach, fourth edition, by Stuart Russell and Peter Novick. Some revision have been done by the authors. So then you can use this latest version Yeah, especially they added some advanced application for this. Yeah. So these are the contents of this book. Yeah, artificial intelligence introduction. Yeah. So I have taken from the previous lecture and also from this book and some materials taken from the other references. Yeah, in order to give the different perspective of the definition or the terminology in AI. And then second one is intelligent agent. Yeah, here. Yeah, for today, agent and environment, good behavior, nature of environment, structure of agent. And I add some materials related to the autonomous system in intelligent agent. And then the next will be the solving problems by searching. So these are all the content of the textbooks. So then you can read and study and explore more about artificial intelligence, especially if you are going to develop the project by using AI. Machine learning for the thesis, mini thesis or thesis for your master degree. So then you can study more, for example, like reinforcement learning. Yeah, because of reinforcement learning actually based on the policy search. But then in this case, we can replace or modify the policy by using the neural network, for example. Communicating, perceiving, and also acting, deep learning, and computer vision, robotic. All right. So these are the content of the textbook. Back to the slide. Can you see slide?
Yes, sir.
Okay, so what is your opinion about agent? Yeah, what does mean agent in your opinion? Yeah, any of you? Just give a comment. What is agent when we talk about the agent? So what is the thing crossing your mind, the agent? Yeah, please comment for this. No problem. There is no wrong opinion, because we have our own argumentation, especially because you are a postgraduate student or master student. So then I encourage you to talk and speak during, give your own opinion or your opinion about the things, the topics and so on. So what is agent in your opinion? When we talk about agent, or you think when we talk about agent, you think about the James Bond like that? No. Martin, what do you think about the agent? Or Aisha? Any idea?
Is it something
Shamil
that
maybe?
helps us?
Yes. Yes, please, Samir.
Is it something that helps us?
It is something one button
Something that helps us.
help us. Okay. All right. So there's something, the things that yeah, maybe have some purposes, right? All right. So any other opinion? It is fine because of you have an idea about the agent. Everyone can have our own idea, yeah, as long as they can give some argumentation about that. Asik maybe? Yeah, right. So back to the slide. Yeah, actually, agent is anything, as said by Samir. Yeah. So something, anything that have maybe some purposes, yeah, for that. So in order to perform the task, yeah, or the objective, yeah, to fulfill the objective of the agent, so it needs perceiving, yeah, perceiving its environment, yeah, yeah. When the agent perceive the environment, so they need this one. They need sensors, yeah, some sensors, and then after the agent, yeah, got some information or perceiving the environment, yeah, by using the sensor, then they will perform action in this case. So the second one, action, yeah. First one, perceiving its environment, yeah, through the sensor. So then agent will collect the information, yeah, from the environment, and after that will perceive, yeah, and the collection of the information from the environment will be done by taken by the sensors, and then the second one is action actually. So agent will do action, yeah, after receiving, yeah, some information from the environment, yeah, then they will perform some necessary action according to the information given, yeah, or according to the processing, yeah, because of the information, then yeah, the data collected by the sensor then will be processed, yeah, by the processor. Then after that will perform some necessary action. So this is the agent, yeah, in this illustration, yeah, the diagram. So the agent. So the agent, we can say, agent consists of the sensors, yeah? So some sensors and actuators, yeah. So yeah, these are the process actually inside, yeah. So because of this, the things inside of the agents, right? So the sensors will collect the data, yeah, the data from the environment. So these are the environment, yeah, and perceived in this case, yeah. And then, yeah, from the sensor will deliver, yeah, to the mind, yeah, or the processor here, yeah, the main system, yeah. So after necessary processes here, and then will deliver or will send the signal to the actuators, yeah, to perform necessary action, yeah, here. So and then back to the environment. So these are the agent works, yeah. So then we can see here. So for the simple example is, let's say the robot here, Yeah, we say the robot as an agent. Yeah. So the robot, yeah, when the robot works or moves, yeah, so then it needs the perception or it needs to collect the data of the environment. Yeah, because of the robot actually, for example, in indoor environment, yeah, indoor. So then the robot needs to know the environment, yeah, yeah. In this case, indoor environment. So then we'll accept, yeah, of the environment. So maybe there is in indoor environment there is open or there is some rooms, yeah, inside of the hall, for example, and then the robot will recognize, yeah, in this case will collect the data, yeah, from the environment first, and then after, yeah, of course, by using the sensor, yeah, here, yeah, maybe a vision, yeah, in this case. So camera, we put the camera, yeah, on the robot, and then after that we'll receive, the viewpoint of the environment, yeah, and then based on this camera, and we'll proceed the data to the process, and the process will define the location, for example, or the position, yeah, of the robot, and after that the processor will send the signal to the actuators and will perform the necessary or some necessary actions, yeah, according to the current environment. So that's why, yeah, so to perform the action it needs actuators here. So like yeah, let's say here leg, yeah, 2 legs robot, yeah, with 2 hands, for example, or 4 legs robot, yeah. So then, or if the robot using the tire, yeah, so then mobile robot with tire, then the robot will move by using the motor with the tire right here. Yeah, so that's why in robot there is the technique, yeah, SLAM, yeah, in order to to understand the situation, the robot. So researchers develop the SLAM, yeah, simultaneous localization and mapping, yeah, yeah. So because of the robot needs to know where is the position actually, yeah, in the middle of the environment, let's say, and after the robot defines the position, then they can move accordingly. And that is an example of the agent here. Yeah. So an agent program runs in cycle. Yeah. Yeah. Cycle of the first one is perceive. Yeah. And think. Yeah. And act. Yeah. Think is actually in the processor here. If we put or we develop by using the processor, yeah, I mean the high performance computing, so then it can think or perform complicated works, yeah, complicated job or complex environment. And then the third one is act. Yeah, so the question is how to get from percept to action. Yeah, that's why this is, yeah, here. So the question, yeah, how to translate, for example, yeah, from the perceive, yeah, to be some action or an action. That is the question. Yeah. All right. So agent function. Yeah, an agent behavior is described by agent function. Yeah, so you know the agent, yeah, given here in the previous slide, and then the agent function, agent behavior is described by agent function actually. So the behavior depends on the agent function. So agent function maps the given perceived, yeah, sequence to action. Yeah, in this case, agent, for example, yeah, human. Yeah, human have, of course, many sensors. Yeah, like eyes. Yeah, so we can see and observe the environment here with eyes, and then ears. Yeah, to hear also the situation. Yeah, and in environment. Yeah. And the actuators, yeah, actuators we can say arms, yeah, fingers, yeah, legs, yeah. So these are considered actuators. And robot, for example, the sensors, yeah, they use a camera, yeah, yeah. Camera is actually, identical with the eyes in human, yeah. So then people develop the sensor that having the similar task with eyes, so they develop the camera to perform this task. And sonar, yeah, sonar is like ultrasound, yeah, based on the ultrasound method, yeah. And then laser, yeah, this is by using the um, lighting, yeah, in order to sense the environment. And then the actuators for robot, for example, we use motors, and manipulators like arm, yeah. Also the leg, for example, that is actuators. And then support, yeah, the example with the coded bit strings and with code bit strings as well, because so it can just simulate the robots on the computer. And the agent function can be implemented by agent program, and it runs on the physical architecture, yeah, to produce action or some action. Yeah. So then we can say agent equal to architecture, yeah, plus program. Yeah. And what is agent function actually? So agent function is abstract mathematical description, and agent program is concrete implementation. It will run on agent architecture, yeah, on the first one, on the here. So then program, of course, will run on the architecture here. Yeah, so that's why an agent consists of architecture and program. Yeah, the program is actually like behavior, yeah, to determine the behavior, yeah, or the activities that need to be performed by agent. Right? This is like mind. Yeah, this is the architecture is the hardware, and the program is, we can consider a software. Yeah, one example here is vacuum cleaner world. Yeah, on vacuum cleaner world, vacuum cleaner can be considered as an agent. So the perception here, the vacuum cleaner will perceive, yeah, the location and contents, yeah, contents of the environment in this case, yeah, yeah. So like maybe dirty or smooth, yeah, or or any object, in the environment, then the location of the vacuum cleaner, and then it will perform some action, for this is vacuum cleaner robot, of course, robot vacuum cleaner that performing the vacuum cleaner, action, that they can do, move left, right, shut, no operation, or stop, so then, these are some action that can be performed by the vacuum cleaner. And then, the first one, this is the first one, second one, and the third one, agent function. It's actually mapping from perception to action. So this is the challenging task actually. So that's why the agent function here actually, represent the behavior of the agent, agent function. So we'll map, based on the percept, the data collected from the environment, and after that perform some action based on the perception. And so these are the illustration, we can say perception sequence and the action. If example A, clean, so then movement or the robot, the vacuum cleaner will move to the right, and if the first one is sequence, right, and then if dirty, so the robot will perform shut, to clean, the dirty environment, for example, dirty tiles here, and be clean and move to the left, and if dirty, for example, and again will perform shut, in order to clean the environment or tile, and then a clean, clean and right, and clean and dirty, shut. Right? So these are some perception sequence that can be generated, based on the task, of this vacuum cleaner agent. And then the function, reflects for a vacuum agent. We say the location and the status, returns and action here. If the status, the condition, we develop the function, based on this kind of the sequence, perception sequence and action. So we can develop this function. If status equal to dirty, then return shut, and else if location A, then return right. If location B, then return left. So that is the function, the possible function that we can develop by using this situation or this description, of the vacuum cleaner. And then the rational agent. So these are similar with the intelligent agent. With, for example, here given a perceptual history, or percept sequence, and action the agent can perform. An agent's knowledge, of the environment. So this is the given or a given condition, or the perception, for the environment. So the agent, a perceptual history. So they have the perceptual history, and also they have actions the agent can perform, and the agent's knowledge, of the environment. This is like a predefined condition, and the performance measure, This is an object criterion, yeah, for success of an agent behavior. So the performance measure, this is the one. So these four conditions are given, yeah, in the rational agent. So in order to perform the task, so they should put some necessary information here, given to the agent. Yeah, so we can say this one as a supervised, yeah, because we put predefined the condition. Yeah, then the agent will process all this condition, yeah, and perceive in real time and do the necessary action, yeah, or drive the actuator to move the agent. Yeah. A rational agent should do the right things, yeah, based on these given factors. And these are the situation or the condition for each possible perceived sequence. A rational agent should select an action that is expected to maximize its performance measure. Yeah, so these are the keyword. Yeah, action, performance measure, given the evidence provided by perceived sequence. Yeah, here, yeah, perceived sequence and whatever built-in knowledge the agent has. And this one. Yeah, so then performance measure, action. Yeah, this is action. Here is performance measure. So these are the condition or the rational agent should do the right things. Yeah. So the agent should elaborate all these given, we can say, measurement or condition. Yeah. Yeah, action, performance measure, percept sequence or history, and also knowledge. And rationality is relative to a performance measure. Yeah. So these are the notes for the rational agent should do the right thing. Right. So performance measure of in this example, yeah, of vacuum cleaner agent could be amount of dirt clean up. Yeah. So the amount of the clean up. Yeah. Amount of the tasks have been done. Yeah. Especially we know the precondition, yeah, or the condition before the agent, yeah, in this case, vacuum cleaner perform the task, and the condition after the vacuum cleaner perform the task. Yeah, so then the performance measure can be the clean up, yeah, amount of time taken, and yeah, amount of electricity consumed, yeah, because of it drives, yeah, the vacuum cleaners. Vacuum cleaners drives by using, for example, the battery or electricity, yeah, and amount of noise generated, yeah, by the vacuum cleaner agent. Right. So better to design performance measures, yeah, according to what one actually want to be achieved in the environment, yeah, rather than according to how one thinks the agent should behave, right? So it is suggested, yeah, or better to design the performance measure, yeah, that is the one. So that's why we should develop the performance measure when we should provide the performance measure when we develop an agent or intelligent agent in this case. So a rational vacuum cleaner agent should clean up the maximum amount, yeah, maximum amount of dirt, yeah, the environment or the tile with minimum amount of time, electricity, and noise. So we can say if the vacuum cleaner agent can perform these things, yeah, maximum amount, yeah, clean up, maximum clean up. This is the keyword: clean up the maximum amount of dirt and minimum amount of time or electricity or noise, then we can say the vacuum cleaner work well. So it depends on the percentage, for example, or the clean up amount of dirt in the environment. All right, so the rationality is not equal to omniscience, yeah, or perfect knowledge, yeah, in this case. So it should be rational. Yeah, an omniscience agent knows the actual outcome of its action and can act accordingly. Right, so it is rational to look both ways before crossing the street. Yeah, that is rational. It is not rational to check for failing spaceship fish. So that is not rational. So when we develop agent, so then we put the rational agent. Yeah, because so the agent will perform according to the rationality. I think now the times for prayer break of over there, right? Duhur time, I think, in Brunei right now, isn't it?
Yes, sir.
Yes, sir.
Right? Okay, so then we take a break for prayer and then we will continue after this. Yeah, around 15 or 20 minutes, right?
Okay, sir.
Right, so we continue the lecture. So can you hear my voice?
Yes, sir.
Okay, so we just finished the rational agent here, and then we continue for the next, specifying the test environment. Yeah, so when we define a rational agent, so we group these properties under performance measure, because of performance measure is important, as mentioned in the rational agent. So instead to see the other things, so we consider the performance measure here, PEAS. So the short form is PEAS, performance measure, environment, yeah, environment, actuators, and sensors. So we define a rational agent and we group these properties under PEAS, yeah, to provide the problem specification for the task environment. All right, so for example, yeah, in the task of designing an automated taxi driver here, so we define the performance measure, yeah, we define the PES, yeah, determine the PES for designing an automated taxi driver. So PES, yeah, performance measure in developing an autonomous taxi driver or automated taxi driver. The first one that we have to consider, yeah, safety, the performance measure. So means that we have to measure the safety, of course, with some necessary tests, for safety testing. So then we can define or determine the safety of this car. And then the other performance measure is time. Yeah, the time. It means the time to reach the destination. How long it will be processed. Yeah, from the beginning. For example, when we call automated taxi or autonomous taxi, and then until the taxi pick up us. Yeah, from the taxi pick up us until the taxi reach the destination. Yeah, so how long the times or taxi takes the time. And legal drive, so because we have to know the policy or the legal status of this taxi. Yeah, in certain countries maybe they don't allow automated taxi drivers yet, but in some other countries they allow this kind of autonomous vehicle. And then the comfort, yeah, so comfortability. So this one, it depends on the, yeah, of course, the design, ergonomic design of the taxi. Yeah, the like user friendly or not. Yeah, in terms of the physical or software and so on. So these are the consideration for the performance measurement. And then the second one, yeah, for considering when we design the automated taxi driver. So we put the environment here. So what kind of environment should be considered? The first one, of course, because of the taxi will move on the road. So we consider the environment. The first one is road. And then the environment of the road, we have to consider the other cars, because on the road there will be so many cars. So then we have to determine the other cars that using the same road. And then pedestrian. So the people that walk, just beside of the road. So then we have to consider this. Yeah, even road signs, yeah, or people cross the road. So all these things, yeah, we have to consider. And customer, yeah, the users, yeah, also very important. So we assume that every people will follow this standard or sign, yeah, signboard, yeah, road sign, and so on. So that's why when people cross the road, yeah, but they don't follow the road sign, then we have to provide the other condition for that. Yeah, yeah. So because of yeah, sometimes. And then actuators, yeah, actuators, yeah, steering wheel, yeah, accelerator, brake, signal, yeah, signal, horn are considered as actuators in this automated or autonomous taxi. So we put this kind of actuators, yeah, when there is an input, yeah, from the sensors, and the car will do necessary action, yeah, give the signal to these actuators. All right. So then the other important things are sensors here. Yeah, sensors, because this is the critical part. Yeah, when we design or develop the autonomous taxi. So in this case, like cameras, you know, we put the cameras and sonar, speedometer, GPS, odometer, accelerometer, engine sensors, and keyboard, for example. So then these all are, yeah, determined and based on, of course, based on the function for each, actuators, yeah, or the necessary information or the necessary data that we can collect, yeah, or the car can be collected, yeah, in order to provide the necessary action through the actuators. So then this should be specified in design of the intelligent agent. Yeah, in this case is autonomous taxi. Right. And the other example, yeah, for PEAS, yeah, the agent in this case, vacuum cleaner, yeah. For example, iRobot Roomba series, yeah, the vacuum cleaner robot. Sorry, yeah, vacuum cleaner robot. So you can see on the market here in the shop, yeah, the types of the vacuum cleaner robot available on the market, and then we have to determine, yeah, we should specify, yeah, the performance measure. Yeah, so PEAS, the first one, performance measure. So how to measure the performance of this robot, yeah, vacuum cleaner robot? The first one is based on cleanness, yeah, cleanness of the environment, of course. Yeah, in this case, yeah, let's say the tiles, yeah, yeah, because of this is just for the vacuum, or maybe the carpet. Yeah. So we can say the cleanness as a performance measure, as one of the performance measures. And then the second one is efficiency. Yeah, efficiency, we can say, or we can determine the efficiency as a distance travel to clean. Yeah, distance travel to clean. So we have to know how is the environment? I mean the size of the environment, for example. Yeah, whether this is the small room or the big rooms, yeah, or one apartment. So then we have to know this situation in order to measure the efficiency, yeah, the distance travel to clean all the rooms or environment. And the other efficiency that we can measure, like battery life, yeah, battery life, and also the security, yeah, the security of the we can say that safety or security of this robot vacuum cleaner. So these are the performance measure, the first one, and the second one we determine the environment, yeah, because of we have to identify in details the environment, like the room, how many rooms should be cleaning by the robot, and how many tables there available, and wood floor or tiles, yeah, and carpet, yeah, and different obstacle exist in the room. So you have to identify these all things, yeah, for environment, because so the robot will move and avoid the obstacle in front of, beside, or behind, yeah, the robot to perform the cleaning service in the room or in the necessary or in the certain location. All right, and then the actuators, yeah, the third one, the actuators like wheels, yeah, wheels of the robot, because of it considered as a, yeah, vacuum cleaner robot is considered as a mobile robot by using wheels, yeah, yeah, and then different brushes, yeah, to perform the cleaning, and vacuum extractor, yeah. So these are the device, yeah, or the function that can be considered as actuator. And then sensors. Sensors consist of a camera, yeah, to recognize the environment, yeah, the object, yeah, like table, yeah, carpet, or wood floor, yeah, for example, and people, yeah, or maybe a pet, yeah, inside of the room. And then a dirt detection sensor, yeah, so to detect the dirt environment, yeah, on the top of the floor, yeah, and cliff sensor, yeah, to climb, yeah, because of maybe the surface of I mean of the room is not the same, yeah, from one side to the other side, so it needs a cliff sensor and bump sensors as well. So when touch the certain object, and the robot can move to avoid and find different road, yeah, in order to finish the task. And infrared wall sensors. So infrared wall sensors to recognize or to detect if there is a wall, then the robot will avoid, will move to different road, yeah, to finish the process. So these are the PES example for vacuum cleaner robot. As you understand in this until this part, do you have any question or any doubt? Yeah, please, you can answer or you can give the comment here. No, still fine. Because of this is not so difficult to understand actually. This is just logic to think about the performance measurement, the environment, the actuators, and the sensors. All right, so the other another example for PS to determine the PS, like the agent, we can say medical diagnosis system. So the performance, the PS for medical diagnosis system is like a healthy patient. Yeah, the first one, and then minimize the cost and loss it. And second one, the environment, can say the patient, hospital, and staff in the hospital. And the third one, actuators, actuators, we can say display, screen display, for the question, test, diagnosis, treatments, referrals, and so on. So then we can see the necessary action that taken or need to be taken, by the patient or staff, here by seeing the screen display. Right, and then sensors, including the keyboard, to enter the symptoms, to find the information or the data, to find the patient answer, and any related things in the medical diagnosis system. So we can use keyboard, to perform these activities in order to sense to collect the information. Because our sensors, basically, the function of the sensor is basically to collect the information from the environment, in this case. Right. And then another example for PES, like the part picking robot. So the performance measure, performance measure, percentage of parts in correct bin. So the percentage of part that pick up or pick by the robot in the correct bins, because of there will be many bins available, various bin with various objects. Then the robot need to picking the part, and put on the appropriate bins or appropriate destination. That is the part picking robot. And then E, for the environment. Environment, of the robot is conveyor belt with parts. So the robot will pick the part on the top of the conveyor belt, and also the bins, because so we'll put the part from the conveyor belt. We'll take the part from the conveyor belt and put on the bins, on the correct bins. And then actuators, what kind of actuators that the agent used? Jointed arm and hand. Jointed arm and hand. So the robot actually a robotic arm with some degrees of freedom. For example, 6 degrees of freedom or 8 degrees of freedom. With arm and hand. In this case, fingers, we can say. We can say as fingers. With the fingers. And then sensors. Sensors, we can use camera, for the sensors, for picking robot. So it uses the camera and join this one, angle sensors. So in order to detect the coordinate position of the arm, the coordinate position of the movement of the arm movement. This is very important because of when we develop this robotic arm, so we have to determine the movement, the possible movement that they can do, the robot can do. So it's called as the path planning. Yeah? So then we have to develop the path planning. Yeah. Then after that, the sensor will check the appropriate path planning, yeah, according to the given program. Yeah, if it is matched with the given program, then means that all the things are right, and proceed the movement accordingly. So it is the sensors. And the other example, PS example, yeah, the agent, interactive English tutor. Yeah, and how to measure the performance of this interactive English tutor in this case. Yeah, in this example. So P performance measure, maximize student score on test. So it is quantitative. It is based on the score on the test. So then the performance measure of this agent, interactive English tutor, is to maximize the student score. For example, before the student joined the interactive English tutor, they got 60, for example, the score, and after following the course from interactive English tutor, then student can score, for example, 80. So it increased from 60 to 80, or maximum score like 90, even 100. So that is the performance measure. And then E, the environment. So the environment is actually set of students. So the numbers of the students here that will be considered as the environment. And then actuators, screen display, for exercises, suggestions, and correction. So it will be displayed on the screen. So then, of course, the some student or set of student will perform the things or the task, based on this information displayed on the screen. And then sensor. Sensor in this case is only keyboard. Even though if we want, we can use also a microphone. For example, if we want, we can put the microphone. Keyboard, microphone. This one. And actuators, instead of a screen display, we can also put speaker, because of maybe the sound or voice of the English tutor, is generated and will be heard by using the speakers or earphone, headset, and so on. And sensor, we can use the microphone in order to interact with the tutor. The student can interact with the tutor. So this is it can be optimize the system. If student can interact with interactive English tutor in this case. Right, so because without speaker and microphone means that this is only single direction of the tutor. So the tutor give the lecture or the class, explain all the things, And after that, the student just see the display and perform or do some exercises as instructed by the tutor. And after finish, give the marks. And after that, finish all the courses. But if we put the speaker and microphone, then the student can do the interaction with the tutor. So it should be more helpful for the student if there is any question or any problems need to be solved or need advice, then student can get the response or advice from the tutor. So now we will discuss about the environment types in this lecture. After we determine the PES, about the performance measure, the first one, and after that continue with the environment types and actuator and also the sensors. All right, so the environment types. So there is some types of the environment that we can say in order to determine the environment or situation and the condition. So fully observable versus a partially observable. So means the agent, in this case is the sensor, give it access to complete state of the environment at each point in time. So then for fully observable means the sensor can access or can collect the information for the complete of the environment, complete state of the environment. And noise or inaccurate sensor, this is observable, fully observable, complete state the environment at each point in the time. And noise or inaccurate sensors or nature of the problem can make the environment partially observable. Due to the inaccurate of the sensors or nature, or the condition, the environment condition, then it can make the environment partially observable. So some of the situation may be hidden by the nature of the problem. So that's why. So the location, the layout, the mapping, so since it is nature, so the sensor or the agent cannot avoid the nature or the environment. So just it can be considered as a partially observable, right? It is a force fully observable and partially observable. And the second types, deterministic versus the stochastic. So the next state of the environment is completely determined by the current states and the action executed by the agent. So if the environment is deterministic or deterministic except for the action of other agent opponent, or the opponents, this one. So this is the current state, determined by the current state and the action executed by agent. Or if the environment is deterministic, except for the action of the other agent or the opponent. So then it's the strategic. So determined, like we can say predefined. So it is the determined, and stochastic, like can say unpredictable. So more sophisticated, in this stochastic environment. All right, so the third one is episodic versus sequential. So the agent's experience is divided into atomic episodes, and each episode consists of agent perceiving and performing a single action. That is the episode, yeah, episodic. Perceiving, and then performing single action. And the choice of action in each episode depends on the episode itself. So the choice or the sequence of each action, it depends on the episode itself. So that is the sequential. So the first one is episodic, yeah, and the second one is sequential. Yeah, for when the agent choice the action for each episode, so it depends on the episode itself. So this is choice of the action. All right. And the next is static versus dynamic. In the environment, when the environment is unchanged while an agent is deliberating. So this is the static or dynamic condition. The environment is semi-dynamic if the environment itself doesn't change with the passage of time, but the agent's performance score does. So that is a dynamic. So then when environment itself change for the dynamic, when semi-dynamic doesn't change with a certain type of passage of the time, but agent performance change. This is a semi-dynamic. Yeah, so for static, the environment is unchanged. Yeah. And then the other types of environment is discrete versus continuous. Yeah, so is the contra of the continuous. Yeah, discrete. Discrete is this is the contra of discrete. So limited number of distinct, clearly defined environment states. Yeah, perceive and action. Yeah. For example, a checker is a discrete environment, while self-driving car evolves in a continuous one. So you can see here, yeah, for self-driving, yeah, or maybe manufacturing, yeah, process, yeah, it can consider as a continuous. Yeah, but checkers, yeah, or yeah, the games, yeah, games usually the games playing games they usually consider as the discrete environment. Right. And then single agent versus multi-agent. An agent operating by itself in an environment or with other. Yeah. So if it is on alone, yeah, or single, then it is a single agent. If they work with other in other or cooperative, yeah, competitive agent, cooperative agent, then it called as a multi-agent with many other agents, yeah, in a single environment. Yeah, that is a single agent and multi-agent. And then the other types is known versus unknown. So the designer of the agent may or may not have knowledge about the environment laws. Is the things. And in a known environment, the outcomes or outcome probabilities, if the environment is stochastic. Yeah, so then if the environment is stochastic, we need to provide the probabilities of the outcomes, yeah, for all action given. If the environment is unknown, then the agent will need to know how it works in order to decide. Yeah, so in order to decide, then agent should know or need to know how it works. That is for unknown environment. All right, so these are examples of environment types, yeah, for each type. So the task environment, yeah, here. Sorry. Yeah, and observable partially or fully, agent, single or multi, deterministic or stochastic, episodic or sequential, yeah, static or semi or dynamic, discrete or continuous. So these are the types of the environment. So for example, the one crossword puzzle, so it is fully, so we can say fully because so we can observe the complete environment, yeah, in crossword puzzle, yeah. And then the agent is single agent because so this is the single, yeah. There is no cooperation or coordination with other agent in this crossword puzzle, and it is deterministic, yeah, not stochastic. So actually, it should, I mean, we can predict the situation, the condition or the environment. And sequential, it is sequential, and it is a static, yeah, and discrete, yeah. So not the continuous one. And chess with the clock, yeah, this one for chess game, yeah. So it consider fully observable, yeah. We can see complete environment, yeah. The board, of course, the chessboard, yeah, with the clock. So it consider fully observable, and the agent is multi agent, yeah, not the single, because of we play with the other agent, yeah. For example, whether it is a computer or a human, yeah. And it is deterministic also, the same as a game. And the episodic is sequential, yeah, because we need to work based on the sequential. And then static, yeah, this is a semi-static, not really, not a fully static, or not dynamic, not 100% dynamic, but consider it can be considered as semi-static. And the discrete or semi-dynamic, we can say. Then it is discrete. Yeah, we can categorize as a discrete, yeah, not the continuous one. So after the end of the game, yeah, one of the I mean the player. So then we end of the game. I mean, if we fulfill the certain condition, then they can immediately the end of the finish the game, yeah, immediately. And the other example like poker, yeah, backgammon games, yeah, these are games on taxi driving, for example, yeah. So we can say taxi driving is yeah, partially observable because of noise or other object, and sometimes the driver cannot see complete environment, yeah, because of hidden or maybe covered by the other object, yeah. So then a taxi driver cannot see or cannot observe the environment completely. That is the thing. And the agent, of course, it is a multi-agent because of the taxi driver will drive the car on the road, and there will be many other objects, yeah, like cars or even small or big cars and motorcycle and so on, yeah, or even people cross the road. And then it should be stochastic because of unpredictable the situation, the environment. Yeah, so then we cannot determine. For example, yes, so of course we expect the people cross the road using the zebra cross, right? But the problem sometimes if there is no zebra cross, there is no I mean like for flyover or pedestrian way of for the pedestrian, for people to cross the road. So then we cannot expect 100% the people will follow this. So it consider a stochastic. So we cannot predict 100% the environment. And the episodic is sequential, yeah. And then The dynamic, in this situation, dynamic or static is 100% dynamic, and then the status is continuous in this one, in taxi driving, until reach the destination and finish the task. And then medical diagnosis is the same, like taxi driving, and image analysis, part picking robot, as we can see here. For image analysis, we can say 100% or fully observable, because of the image we take, for example, the image taken 100% observable, and then the agent is single and deterministic and episodic, semi-dynamic and continuous also. And for part picking robot, the environment is actually the partially observable. This is similar like a taxi driving, because of part picking robot, they sometimes they cannot see the environment completely, due to the other object or the nature of the environment, of the condition, the layout, and so on. And then the agent, since it works alone, so a part picking robot consider a single agent, and because of no collaboration in this task. And this is the stochastic, episodic also, and dynamic. It is the dynamic environment, and continuous. And the other examples like refinery controller and interactive English tutor. So you can see here the environment types for each example. So in here, how about the ping pong playing robot? So can you give the idea for the ping pong playing robot? I have shown in the first class, in the first meeting, about the ping pong playing robot. So what do you think? How about the ping pong playing robot in terms of observable, partially or fully, agent for sure. Agent for sure. What is for agent? It is it a single or multi for ping pong playing robot? Multi, all right. Yes, green. So because of the agent is not playing alone. So because of agent will play with the counterpart of course, against the robot in this case. Human against the robot. And then it can be also double, double robot and double human. So can be 4 agents in this case. Or robot with robot also possible. Double robot and double robot. So robot can be against of the human, or double or single, or robot against robot. This is the ping pong playing robot. And how about the in terms of observability? It is partially or fully? What do you think for ping pong playing robot? Is it partially, we can say? Or fully?
Fully.
Fully, yes, right. Because of we can see completely the environment of the ping pong, the area of the game, in this case. So there is nothing hidden, or hide or covered by the object. We can see completely, because of the ping pong table is actually small, not big. So then human or robot can see completely 100% all the area. Right, and then in terms of deterministic, it is deterministic or stochastic, can say?
Stochastic.
Stochastic. Why if you say the stochastic?
Our when we hit the ping pong ball, it's not always accurately where we want the ball to be landed.
Yeah, that is the thing, right? Because of the area, we do not determine the area, only the size of the area. That is different with the chess. Chess, we can say the chess, we can predict, yeah, where the next movement, yeah, for each was it like a king or you know, when you play the chess, we can predict where the next movement of the game, yeah, right. But then for ping pong, since the area is not really small, yeah, but we can see all, yeah, completely, even though we can say this is fully observable, but the location of the ball hit of the table, we cannot 100% predict, yeah. And that is the thing, the situation. Yeah, episodic, discrete, static, yeah, this one. So consider as the dynamic, right? Do you think about the static or dynamic? Aisha or Samir, can you give opinion about the ping pong robot? It considered as a static or dynamic or semi?
Is it static?
Static? Why you say static?
Is it because the ping pong board is the same environment?
Yeah, yeah, you are right in the environment, but actually the condition depends on the, you know, we can say it is one like a semi dynamic, yeah, like the chess board, yeah, because of sometimes there is a unintended situation, yeah, especially for the multi-agent, yeah, for many players, yeah, double. So consider not really static, not 100% static, but it's fine if one and one again one, maybe we can say like static, yeah. But if double, we can say almost dynamic. That is the situation. All right, so that is ping pong, and the environment type largely determines the agent design. Yeah, this is the conclusion. So the real world, yeah, partially observable, stochastic, yeah, sequential, dynamic, continuous, and multi-agent, right? So that is a ping pong playing robot, yeah. So then we can say this is dynamic, yeah, in terms of the double or more than not single player, but multi with many with two, yeah, double, two players. All right. So this is the basic skeleton of the agent, yeah, for agent types, function, skeleton, agent, yeah. Yeah, the perception and returns the action, yeah, the static or the memory, the agent's memory of the world, and the memory status, we update the memory, memory and perceive, yeah, and action, choose the best action, yeah, for the action, and the memory again update the memory for the action. So the first time the memory will perceive, yeah, perceiving of the environment, and after that take the necessary action, yeah, the memory choose the best action, yeah, according to the memory perceive, yeah, or perceiving, and the memory will perform an action based on update the memory and return the action. So that is the skeleton of the agent, and four basic types in order of increasing the generality. yeah, of the agent. There is a simple reflex agent and model-based reflex agent, a goal-based agent, and utility-based agent. Yeah, that is the basic types in order of increasing generality, and all of which can be generalized into learning agent that can improve their performance, and they can generate the better action. So this is the diagram of the simple reflex agent. Yeah, yeah, the agent, and this is the environment. Yeah, yeah. So just keep in your mind that when we deal with the agent, so then we have to consider the environment, right? So that is the system that we should provide, the agent and environment, the interaction between agent and environment. So in environment, so the agent, yeah, there is some sensors, yeah, from the agent that will collect the data from the environment. Yeah, sense the environment and situation and what the world is like. Yeah, no. So based on the sensor, and then what action should do now. Yeah. So after got the perception, then the agent will decide the action should do, and then provide the signal to the actuators here. Then actuators give back to the environment. So that is like cycle here. Yeah. Cycle. Then back again to the agent. So simple reflex agent select an action based on the current state only. So that is the simple reflex. Yeah. So only based on the current state and ignoring the percept history. That is a simple reflex. So it doesn't care about the perception history, the history of perceiving. Yeah. So then immediately will perform an action, yeah, that they should do, and it is simple but limited. Yeah, very limited. And then the actions determined using if then rules condition. Yeah, if condition then action, if then rules. So this is the action. Yeah, so determined by using the simple if then rule condition. Like if car in front is braking, then initiate braking. Yeah, so when the condition the car stop, then we start also, we do the stop also for the car. So that is the if then rules condition, right? And then the second model is a model-based reflex agent. So in simple reflex agent are admirable, but have limited intelligence, yeah, especially when the environment is partially observable. Yeah, so car in front is braking is difficult to be determined from current perception only. Yeah, without perception history, that is the thing. So without perception history, it is a very difficult. Yeah, so then that's why in simple reflex agent, it is a simple but very limited. Yeah. So in model-based reflex agent, so we can see here, this is the environment and this is the agent. So the sensors will collect the data or from the environment here. Yeah. And then what the world is like now. So there is a state, yeah, and how the world evolves and what my action do. This is for model-based reflex agent. So they start to build the model based on this. And then after that, what action should do now. So it is based on the condition action rules. Yeah, not if then rules. This one, yeah, condition action rules, yeah, only based on the if then rules. Yeah. So then we see the condition action here. So model based agent maintains internal state that depends on the perceived story. So that is the thing, the different. Yeah, in simple reflex, it doesn't care with the perceived story. Yeah, so it doesn't consider the perceived story. But in model based, yes, we'll consider the perceived story. So it depends on the perceived story to reflect some of unobserved aspect, especially because of not all environment are observable. Yeah, it is partially observable. So to reflect some the unobserved aspect of the current state, they provide this model based, yeah, with a model that describe how the world evolves independently of the agent and how its actions affect the world. Yeah, that is the model based reflect agent. And then the third one is goal based agent here. Yeah, so this is the environment. Yeah, the agent. So the sensors will collect the data from environment. Yeah. Yeah, and then what the world is like now and what it will be like if I do action A. Yeah, the condition. So it consider the state, how the world evolves, and what my action do. And after that, what action I should do now. So this relates to the goals. Yeah. So knowing the current, and after that, send the signal to actuators. So knowing the current environment state is not always enough. Yeah, to decide what to do next. Yeah, after receiving the data from the sensors or the environment. Consider the future with what will happen if I do A. Yeah, for example, I do action A. So then the agent will consider this for the future. Yeah, for the future movement. Yeah. So what will happen if I do A? And a goal-based agent, yeah, this is the goal-based agent keeps track of the world state, yeah, as well as a set of goals and trying to achieve and choose an action that will lead to the achievement of each goal. Yeah. So it uses search and planning to find the sequence. Yeah. So this is the goal-based agent. So it depends on the goal, yeah, of the agent, and it will choose an action lead to the achievement of each goal. That is the thing. Yeah. And then the fourth one is a utility-based agent. So it is more complex. Yeah. So with the environment, then the agent as usual, and the sensors will collect data from the environment, and it will construct what the world is like now, and what it will be like if do action A, for example, and how happy will be in such a state, what action should do now. Yeah, and then go to the actuators and perform the necessary action. Yeah, so for the beginning, what the world is like. So there is a state, yeah, affected or influenced by the state, and how the world evolves, and what my action do. Yeah, that is related not only for the determining the world, yeah, but also will be like if I do action. Yeah. So what my action do, and also how the world evolves. And then for how happy I will be in such state, consider it relates to the utility here. Yeah. And then what action I should do now, will relate to the actuator. So sometimes achieving the desired goal is not enough. Yeah, we may look so not enough to consider only the desired goal. So we may look for quicker, safer, cheaper to reach the destination. That is the thing. And then for high quality behavior, utility-based agent uses a model of the world, yeah, along with a utility function, and measures preferences among states of the world. And due to the uncertainty, yeah, it chooses the action of leads to the best expected utility. And this is the interesting agent, yeah, robot soccer agent. Yeah, I have experience with the robot soccer because of in 2012, yeah, we went to UK, yeah, Bristol, to perform. To join the World Cup robot soccer in UK at that time. I was with University Kebangsaan Malaysia at that time. Then we won the second place, yeah, for robot soccer World Cup, yeah, in UK. So I have a lot of experience with this robot soccer agent. Yeah, even the video that we played the game, yeah, at the beginning we played the game against the Indian Institute of Technology, yeah, in Madras, IIT Madras. And second game we against one university in South Korea. I think during the semi-final we against the Sungkyukwon University from South Korea, and in final we against we did again with the match was between UKM and one university in China. Yeah, the University of Technology. I do not remember exactly the name. Beijing University of Technology or something like that. And yeah, we got the second place. Yeah, we lost in the final against the China teams at the time. And then the robot soccer agent, yeah, the performance measure, when we determine the performance measure, yeah, of course, the objective or the purpose is to win the game and to score the goals, yeah, because this is the robot playing soccer, yeah. So actually there is many types of the robot soccer, yeah. One of the types is what's it, the small size robot soccer, yeah, micro robotic, yeah. So that is a small size, yeah, with wheel, yeah, robot wheel. So 4 players, yeah, sorry, five again, 5, yeah. So 4 players with 1 goalkeeper and 4 players with 1 goalkeeper. So 5 against 5. 4 against 4, I think, because of goalkeeper are also the task of the defender. So 2 defender and 2 midfielder, yeah, or attacker. So only 4 against 4, not 5 against 5, but 4 against 4, because of the function of goalkeeper combined with the defender. Prevent opposition from scoring. So these are the measure, yeah, of the performance for robot soccer. And the environment, yeah, real or simulated, yeah, robot soccer field, yeah, soccer field at that time. Yeah, of course, we use real time, the real environment of the robot soccer. We use the board, yeah, the big one, like the area or like the mini stadium, yeah, to perform the robot soccer. And then the actuators, yeah, kick, dash, and turn. Yeah, that is the actuators. And the sensors, yeah. So use a ball position, goal position, and other players. Yeah. So we use some sensors for this, yeah. And the communication using Bluetooth actually, but to know the position, ball position, goal position, and other players, we have to count by using the coordinate position. We use the vision sensor, yeah, in order to collect the data of this environment, yeah, like ball position, goal position, other players. So we use the vision sensor. So we use a camera here. So it depends on the types of camera, but we use a CCD camera, yeah, the high speed camera. We cannot use what's that, the CMOS, yeah, the webcam, because a webcam is very low performance, yeah, with only 30, maximum 30 frame per second. But for robot soccer, we need a high performance camera with a high speed resolution, yeah, or frame per second. Right, so how can the soccer player be implemented as agent? Yeah, so what kind of agent that we can use? Either we can use simple reflex agent, or model-based reflex agent, or goal-based agent, or utility-based agent. So building a real soccer player is currently beyond the state of the art. Yeah. However, many of the technologies already exist. And then the learning agent. Yeah, here how agent programs come into being. Yeah, so we can program them by hand or teach them. That is learning agent. So learning agent become more competent and improve their behavior by experience. So the performance elements, selection, action to take. Yeah, so that is the learning agent here. So the environment, the agent, and the sensor will take the data, collect the data. Yeah, and then there is a performance standard, yeah, here, and critic, yeah, for the learning agent. Give the feedback inside and give the learning element. So the performance element will change, yeah, depends on the learning element. One element will give the knowledge, and a learning element will give the change. Yeah. And then learning element will give the learning goals, yeah, problem generator, and back to the performance element. And the actuator will provide the necessary action for the robot. And agent organization, so it is focusing on a particular component of an agent, such as the one that deals with the many action do. So we have different ways such component can represent the environment. Yeah, so those attention might be represented differently along an axis of increasing complexity, expressive power, atomic, yeah, vector, or structure. So you can see here the A part is atomic, yeah, for organization, and the second part B is vector and structure, the third part. Yeah, so what is atomic representation? So its state of the word is a black box that has no internal structure. That is the meaning of the atomic representation. So finding a driving road on the map of cities, each state is city. Yeah, and algorithm, search, game playing, Markov decision processes mostly work with atomic representation. And factor representation, each state has some attributes or value properties here. Yeah. The relationship between the object of a state can be explicitly expressed. So when we need to understand the word as having things that are related to each other. And for AI algorithm, we use, let's say, first order logic knowledge-based learning, and NL understanding. So natural language understanding. All right, so this is the summary of this lecture for the intelligent agent. So there is terms, some terms for in this lecture, like agent, sensors, actuators, agent function, and the rational agent and performance measure. And task environment, and also we introduce the PAS, performance measure, environment, actuators, and sensors, and properties of the task environment, whether it is fully observable or partially observable, or deterministic, stochastic versus stochastic, episodic versus sequential, static versus dynamic, discrete versus continuous, single agent versus multi-agent. And the agent type, whether it is simple reflex agent or model-based reflex agent, goal-based agent, utility-based agent, or learning agent. All right. So that is a summary. Any question or comment for this topic? The second lecture about the intelligent agent. I just want to give some perspective about autonomous agent, or in the robotic application. So an agent is actually, this is the computer system that is capable of independent or autonomous action on behalf of each user or owner. So this is an agent, in this autonomous agent. So actually, the computer system that is capable of to perform the some independent actions, on behalf of each user or owner. That is autonomous agent. And then this one illustration here, when the space probe makes long flight from Earth to outer planets. So the destination is outer planets here, and decide how to deal with unexpected environment, or eventualities. So then we define the starting point from the Earth, and then from the launcher, of course, and then the destination. So define the destination, and then this space should tackle or handle with unexpected environment or eventualities, because it is the first time that they fly, and we don't have any record or history of that. So we compare between the teleoperation and autonomy. What does it mean? Many autonomous vehicles are not really autonomous. So we have to define the meaning of the autonomous here. So the autonomous robot make their own decision. That is the thing. So we have to differentiate between autonomous and teleoperated. So this one we can say in the picture in the left side, we can say autonomous, and the right side we can say teleoperated. So the teleoperated means that the people will control the movement, like the remote control, then will give the instruction according of the the goal or the destination. So what is an agent here? The main point about agent is they are autonomous. That is the point. Capable independent action. So an agent is computer system that is situated in some environment, and that is capable of autonomous action. That environment in order to meet the delegated objective, in order to achieve the goals or the purpose. And it is about the decision, all about the decision. Agent has to choose what action to perform, and agent has to decide when to perform. So this is the same actually for the robot, so agent and environment. So this agent, for example, they have, it has some sensors. It has some sensors, for percepts, and effector, or actuator, for actions. Effectors or actuators, you can say. So the fundamental question is what action to take for a given state of the environment. And then what is mobile robotic here? So in mobile robotic becomes the question. This is the SLAM actually. Simultaneous, a localization and mapping. Where am I? Where am I going? How do I get there? So the robotics part should answer this question. So this is autonomy. There is a spectrum of autonomy from the simple machines, no autonomy, until the people with full autonomy. So our autonomy is actually adjustable. So decision handed to higher authority when this is beneficial. That is autonomy. For simple uninteresting agent, like thermostat, for example, delegated goal is maintain the room temperature, and action are heat on off. And Unix speed program, delegated goal is monitor for incoming email, and flag action are GUI action. They are still trivial, so a simple thing, because the decision making they do is also trivial or simple, very, very simple. So intelligent agent, typically think of intelligent agent as exhibiting three types of the behavior. These three types of the behavior that we can say exhibiting of the intelligent agent: proactive, reactive, and social ability. The proactive, goal-driven, reactive, environment-aware, and social ability. So these are the definition of proactive. Reacting to an environment is easy, but we generally want agent to do things for us. This is the thing, the one, the goal-directed behavior. And proactiveness, generating and attempting to achieve goals, not driven solely by even taking the initiative. And reactivity, this one. So these are the characteristics of intelligent agent. Proactive, reactive. If a program environment is guaranteed to be fixed, program can just execute blindly. That is a reactive. A reactive system is one that maintains an ongoing interaction with its environment and respond to change that occur. And social ability, the third one, after reactivity. The real word is a multi-agent environment actually. So as we know, the word is multi-agent environment, then we cannot go around attempting to achieve goals without taking other into account. That is the thing. So some goals can only be achieved by interacting with others. Similarly, for many computers environment, witness the internet. And the social ability in agent is actually the ability to interact, with other agent. Of course, in this case, via cooperation, coordination, and negotiation. Right. So that is the characteristic. We take this part only until the characteristic of the intelligent agent, because it is very important. Proactive, reactive, and the social ability. It is some modeling actually for intelligent agent. We do not deal with this kind of architecture for agent. We want to know more, then I can give you this slide as well. For the second part. So for the architecture for the agent. Right. So abstract architecture for agent. The runs, for example. it is more complex still, yeah, because all of the runs pictures start from the same state. This is environment, so this is the model of the environment. The agent, yeah. We can think of an agent as being a function which map runs to action like this. Example is an agent. And then the system itself, we can consider the system like this, yeah, with the model R, AG, agent, and environment. So I assume R, yeah, for AG, environment contains only runs that have ended. This is the system, yeah. And then the notation. Deliberative agent, yeah, is the potentially the agent will reach a different decision when it reach the same state by different routes. And purely reactive agent, purely reactive agent with state, yeah, perception. All right, this is a robot with state, yeah, 4. And then, okay, these are same like as mentioned, similar, but this is focusing on the robot actually for general control architecture. Yeah. Okay, so any question?